In exercise 1 to 5, we need to find the characteristic polynomial and the eigenvalues of the matrices. So we know that for the characteristic polynomial, that means we need to find determinant of a minus lambda I. For the characteristic polynomial equation, we need to find determinant of a minus lambda I is equal to 0, and then we need to find what is the eigenvalues. So for number 1, which is this one, so the characteristic polynomial, first we need to find a minus lambda I. So a minus lambda I, the determinant, is equal determinant of 2 minus lambda 7, here 7, and 2 minus lambda. Now the determinant of this one is just 2 minus lambda multiplied by 2 minus lambda, so this is 2 minus lambda all square. Then minus 7 multiplied by 7, 49. So if we expand this one, we get it is equal lambda square minus 4 lambda, and here we have 4 minus 49, so this is minus 45. So this is the characteristic polynomial. So characteristic polynomial, this one. Now the characteristic equation, just we need to put this one is equal to 0 and solve it for lambda. So now lambda square minus 4 lambda minus 45 is equal to 0. So from here lambda minus 9 and lambda plus 5 is equal to 0. So either lambda is equal to 9 or lambda is equal minus 5. So this is the corresponding eigenvalue of the matrix in 1. We do the same thing in 3 and 5, and we find the characteristic polynomial, finding the characteristic equation. So as we did in 1, we also do the same thing in 3. We find first characteristic polynomial, determinant of a minus lambda I, so this is the characteristic polynomial. Then we need to write the characteristic equation and solve this one for lambda. We use this rule to find what is lambda. Lambda is equal minus b plus or minus root b square minus 4ac over 2a. And we find that lambda is equal 1 plus or minus root 2. Also, we did the same thing for 5. First, we find a minus lambda I, which is 2 minus lambda minus 1, 1, 4 minus lambda. After that, then we find the determinant. So this is the characteristic equation, the characteristic polynomial. To find the eigenvalues, we write the characteristic polynomial equation, which is this one. We put this one equal to 0, and then we solve for lambda. So lambda is equal 3, lambda is equal 3, or we can write it as lambda is equal 3 with multiplicity 2. In 7 also we need to find the characteristic polynomial. So we need to find the determinant of a minus lambda I. This one is the characteristic polynomial. To find the eigenvalues, first we write the characteristic equation. We solve the characteristic equation for lambda using the general rule. So from here lambda is equal 9 plus or minus root minus 47 over 2. We said before that lambda can be real number, can be complex number. So once you find here root minus 47, don't say that lambda has no solution or there is no solution for this equation. No. We said that before lambda can be positive, lambda can be negative, lambda can be complex number or real number. In exercise 9 to 13, we need to find the characteristic equation or characteristic polynomial, And here we have a 3 by 3 matrix, so that means we need to find the determinant either using properties or technique in section 3.1 or using the cofactor. So for 9, let us find first a minus lambda I. So this will be equal, without determinant. First let us write it A minus lambda I. So this is the matrix 1 minus lambda 2 0 0 3 minus lambda 6 minus 1 minus 1 0. Now finding, sorry, this one is not 0, 0 minus lambda, so it will be minus lambda. So to find now the characteristic polynomial, that means we need to find the determinant of A minus lambda I, which is the determinant of this one. So if we use the technique in 3.1, we can take the determinant by the first row, for example. So through the first row, we'll find the determinant. So the determinant will be 1 minus lambda multiplied by determinant of, we cross this one, so 3 minus lambda minus 1, 6 minus lambda, then 0, so minus, the first one plus, the second one minus, 0 multiplied by, so this one will give us 0, so let us write it 0 just only. Then the third one will be plus, here we have minus 1, the determinant of, we cross this column, cross this row, we have 2, 3 minus lambda, then 0 and 6. So now just we need to find this one, so this will give us 1 minus lambda multiplied by the determinant of this one, so it will be minus lambda multiplied by 3 minus lambda, and then we subtract minus 1 multiplied by 6 minus 6, and here we have 6, so this one will be plus 6. Then for this one is 0, then this one is minus, so 2 multiplied by 6, it is 12, minus 3 minus lambda multiplied by 0, so this one will be 0. So now just we need to simplify this one. It will be, after simplification, multiply 1 minus lambda by this bracket. For this one, what is this one? 3 minus lambda. So after multiplication and simplification of this one, you will find it is equal minus lambda cube plus 4 lambda square minus 9 lambda minus 6. So this is the characteristic polynomial of the given matrix. Now we'll do the same thing for 11 and 13. So here for 11, first we find A minus lambda I, then we find the determinant of A minus lambda I through the first row, because we have two zeros, so it is easy to find the determinant using the first row. 4 minus lambda, then we cross this one, we have this matrix. We cross this one, we have this matrix, which is 3 minus lambda 0, 2 minus lambda. Finding the determinant and simplify, we find this one, the characteristic polynomial. Similarly for 13, first we find A minus lambda I, then we find the determinant through the third column, because we have here two zeros. So since we have two zeros, it's better to take it through the third column, because we get here 0, then just we need to find the determinant of 3 minus lambda multiplied by this matrix 6 minus lambda minus 2 minus 2, 9 minus lambda. After simplification, we will get this is the characteristic polynomial for the given matrix. In 15, list the eigenvalues repeated according to their multiplicity. So this matrix is an upper triangular matrix, and according to the theorem, the eigenvalues of the triangular matrix are all entries in the main diagonal. So from here, lambda will be equal 4, 3, then 3, then 1. Or we could write it 4, 3 will multiplicity 2, and 1. And because this one is the triangular matrix, we cannot do this one for any matrix. It should be triangular, either upper triangular or lower triangular. In 20, use a property of determinants to show that A and A transpose have the same characteristic polynomial. That means we need to show that A transpose minus lambda I is equal the determinant of A minus lambda I. So first let us start by left hand side, and then we want to show that the left hand side is equal to the right hand side. So left hand side, determinant of A transpose minus lambda I is equal determinant of A transpose minus lambda I transpose. Why we write this one I transpose rather than I? Because we know that I and I transpose are the same. So then using the property of the determinant, this is just, and the transpose, this is just the determinant of A minus lambda I all transpose. Because according to the property of the transpose, we can distribute this one to be A transpose minus lambda I transpose. So this one is equal. We know that the determinant of A and the determinant of A transpose are equal. Similarly, determinant of A minus lambda I transpose, it should be equal determinant of A minus lambda I. And this is just equal to the right hand side. So from this step to this step, we know that determinant of A is equal determinant of A transpose. So similarly, determinant of A minus lambda I transpose should be equal determinant of A minus lambda I. And this is by theorem 3. So we showed that a determinant of A minus lambda I is equal determinant of A transpose minus lambda I. So they share the same characteristic polynomial. In exercises 21 and 22, A and B are n by n matrices. Mark each statement true or false, justify each answer. So A, the determinant of A is the product of the diagonal entries in A. This one is false. If A is a triangular matrix, then the determinant is the product of the diagonal entries. But since A is not a triangular matrix, so we cannot say this one. So false. A should be a triangular matrix. The determinant of a triangular matrix A is the product of the diagonal entries in A. B, an elementary row operation on A does not change the determinant. This one is false because the determinant change if we do row interchange or if we do multiply a row by scalar C. So this one is false. Then C, determinant of A multiplied by determinant of B is equal determinant of AB. This one is true because it is from the properties. D, if lambda plus 5 is a factor of characteristic polynomial of A, then 5 is an eigenvalue of A. This one should be false. We solve lambda plus 5 is equal to 0, so that means lambda is equal minus 5, not 5. Now for 22, if A is a 3 by 3 with columns A1, A2 and A3, then determinant of A equals the volume of the paraboloid determined by A1, A2 and A3. We said that the determinant of A is the volume of a 3 by 3 matrix if we take the absolute value, and here there is no an absolute value, so this one is false. So we said it is a determinant, but we take the absolute value because we don't have, because the determinant could be positive, negative, and since we talk about the volume, so we need to take an absolute value of the determinant. An absolute value of a determinant. Now B, determinant of A transpose is equal minus determinant of A. We said this one is false. Determinant of A is equal determinant of A transpose. Then C, the multiplicity of a root R of the characteristic equation of A is called the algebraic multiplicity of R as an eigenvalue. This one is true. So C is true. Now for D, a row replacement operation on A does not change the eigenvalues. We know that row replacement changes the determinants by minus sign, and the eigenvalues depends on the determinant. So if we do if we do row replacement, that means the determinant will be changed and the eigenvalue will be changed. So this one is false. In 24, show that if A and B are similar, then determinant of A is equal determinant of B. Since A and B are similar, so we can write A is equal B inverse for invertible matrix B. Now we want to show that determinant of A is equal determinant of B. Let us add determinant for both sides. So determinant of A is equal determinant of B inverse. So now using the properties of the determinant, this can be written as determinant of B, determinant of B, and determinant of B inverse. So now this one is a scalar, this one is scalar, this one is a scalar. So ABC, it is equal CAB, it is equal ABC, sorry, CBA. So we can interchange between a scalar for all scalar ABC. Similarly, since this one is scalar, 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 so we can write this one as determinant of B multiplied by determinant of P inverse multiplied by determinant of B. Now this one and this one, because both of them is determinant, we can again use the determinant properties. This is just determinant of P inverse multiplied by determinant of B. We know that B and B inverse is just the identity, so this is the determinant of the identity matrix, determinant of B. And we know that the determinant of the identity, it is equal just to 1. So 1 multiplied by determinant of B, this will give us determinant of B. So we show that determinant of A is equal determinant of B.